Now, so yes, the recording is happening. So, questions of any sort?
Yeah, I have a question regarding the homework.
Yeah,
I noticed it was chapters 8, 9, and 10. Is that correct?
8 and 9 for sure. The
Okay.
chapter 10, I'm not thinking that I want to assign those problems, but after class today, it's a maybe.
Okay. So just
The
stay tuned.
chapter, yeah, the chapter 10 content, there's only one real question in chapter 10 in our text that I like to assign, and I don't like the question very much at all. And so it's a matter of whether I want to bite the bullet and assign that the way I typically have, or whether I have the time shortly following class to come up with what I think is a better class of questions that are based on real data rather than just there's some X and we're going to do this with it. But yeah, that question I think is a good one. It's just that it's so divorced from reality of any real data set. I'm wondering if I could just rewrite the basic parts of it with a real life data set where it would matter. Yeah, so thank you for mentioning that, Jack.
I also had a question about homework. Does your grader have any clue when they might get some of our homework graded?
No. Well, okay, no. I don't know if she does, but I do know that I don't because I've attempted to interact with this grader, and the last time she said, "Oh yeah, 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 I'll do something," and she made a tiny amount of progress with the other class, but nothing on this one. So I'm frustrated. I can't do anything about that. And to be honest, I don't have the time in my life right now to go ahead and start the grading of your stuff. So, with that in mind, I guess apologies for me are in order, but I can't force someone else to do what they're supposed to do. Isn't that frustrating that you don't get to just control other people? I hate that. Like, if I could magically turn a switch and you'd all just like learn it and know it without any hassles, I would do that. But yeah, sometimes life has challenges. Like, it's hard to learn some stuff, especially if the grader doesn't get certain feedback to you.
Following up on that,
Yeah,
when
yeah.
do we have to decide what final we want to take?
Yeah, good question. And that's what I can answer. So let's go with that. Um, right around the end of week 9, I should have to each and every one of you here's what your grade is today. If I had to assign a grade to you today, here's what the grade would be. And a statement like, for you to get at least a blank in the class, here's what you'd have to do on the final exam. But if you do below, then fill in another blank, here's what your grade would be. So I'll try and tell you where you're at right now, how much you need to do better to get a slightly better grade, usually like a third of a grade. Like if you're clocking an A minus now, what would it would take to get an A? But what would it be for you to get a B plus instead of an A minus? And I'll do that probably via an Excel spreadsheet where you just enter your scores in for various course components, and it'll just automatically calculate for you where you're going to be under each of the two separate options of taking the two-part final, okay, or the final that's on just the most recent material alone. So by the end of next week is about when I should have that to you, and you'll have a full week to make a decision, talk to me about it in greater depth if you'd like to. And then eventually you guys make a decision, and here's how it works. If you only take one part of the test, I know exactly what you did. If you choose to take the part for everyone, part E for everybody, and then also choose to then take the comprehensive edition, that works. I don't care. That's absolutely fine. If you think that you really want to do that, I'd encourage you to do that. But it can have the impact of lowering your grade a little bit. and you'll get some guidance by the end of next week on that. Does that answer your question, Daniel? Now, I know there was someone else who was going to say something right around the time that Daniel did say something. And if you were the one who was saying something, then muted yourself, because that awkward thing when like two people are talking at once, you can't all do that. Now's your turn.
Yeah, I just went to go download the lab, and when I download it, it just downloads the lab that we had on Tuesday.
Okay, so I'll fix that
Okay.
soon. I was in a meeting right before class started and then thought right at noon, oh shit, I forgot to upload the lab, and so I probably should make that change.
No
So
worries.
I'll make that. Well, yeah, do I look worried?
Thank
No,
you.
but yeah, I do appreciate those reminders because that's the sort of thing that helps you get the lab done. And so, so right around the time, right between the end of sort of the lecture portion and then the beginning of the next section of class is when I'll be focusing on that. Now, was it you click your way into Lab 8B?
So when I click it, it just refreshes back to the week 8.
Oh,
And
yeah,
then
yeah, I see that.
It just re-downloads week 8A partial.
Yep.
test.
Where I clicked edit, I probably hit cancel after making my edits. And so I'm going to redo that very soon.
Thank you.
Okay, so things to do, short list. Hopefully it's a short list. Okay, so yeah, that is definitely the problem. Hold on. I might be able to get this fixed right quick because I did actually save Lab 8B, but that one link itself was the problem. So I'll change that link, and I'll do that like right now while we're talking. Okay, so thank you for mentioning that. Is someone else maybe while I'm pointing and clicking? And hopefully this will work. Darn it. Course links. Wrong. I hate this. Okay, so I'm just going to sort of take this time right now and get it done properly because otherwise that will be perhaps bad later. Okay, and I'm not sharing the screen yet, so you're not watching me be embarrassed in front of you. Okay, course links. Not pages. Ah, that's it. And that should be now done. So I'm presumably at least one of you will check, and if things work now, that's great. If they don't work now, that it actually is this next lab, someone let me know, and we'll get it fixed when we can.
It works if
Ooh,
horse
that
semen.
was yeah, that is an awkward data set. I'm going to say some of you animal science sorts of people, or maybe you know animal science people, there was a faculty member, Bill Plummer, who still hangs out on campus sometimes, but what he did was equine, breeding research, which essentially, yeah, you don't want to have as a statistician his students come to your office and show you the videotape of how they collected their data. But they did sort of go with a study, and this is, I'll just tell you about the study right now because you're going to be doing it in the lab. They collected data on whether using a particular chemical increases the motility of horse semen. Motility means just think percent swimminess, okay, versus dead. And you would like to have the motility remain high for a long period of time, because that way you could then sell the horse semen to someone who wants to, well, get a new racehorse. You could sell the horse semen of your thoroughbred and sell it for more if you can promise a certain percent motility. Okay? And so this chemical should maybe help. And then there are two ways of selling horse semen. One of them is frozen. Literally, it could be frozen. And then the other, and I believe we called that cooled. And then fresh means it's refrigerated to just above freezing, but it's not yet freezing. And so you'd think whether you freeze it or not may impact the motility, but also the amount of time that's gone by since the collection of the horse semen may impact the motility. And so the ultimate goal is, what is the best way to treat this horse semen before you sell it? One of the methods is use the chemical and then freeze it. Use the chemical but don't freeze it. Don't use the chemical but freeze it. Don't use the chemical and don't freeze it are the four options. But there is this time decay. Presumably horse semen is going to change slowly in its motility over time. And how we model that is actually the point of the discussion today. So let's dive right in, unless one of you has additional questions right away. Looking around the room on this screen.
How do they assess the viability of the gametes?
Microscope.
Will they germinate it?
Oh, horse semen. And viability is measured by percent of the horse semen that's literally swimming.
Gotcha.
So you take a little bit and you stick it on a little plate, glass plate, squish something on top of it, and then you put it underneath a microscope, and you got a little circle, and you say, okay, there's 57 of them, and 42 are swimming. You take a ratio, you're good to go. So clearly, there's data that's measured with error, because if you had just literally moved the microscope over a little bit, the slide over on the microscope, you would have had a different collection of horse semen, living and dead, that you were looking at. And so the exact percent swimminess is measured with error relative to the truth. And then there's also other sources of error in the process of collecting the data, but there is a general trend that you can spot. Maybe another question? Okay, so I've got control of the window in front of you, or at least I should be displaying something. And if I remember geometry from high school, if I had a plane and I've got 2 points in the plane with different values for x, and that's sort of an important thing, I could connect the dots and keep going, and I have a straight line. 2 points determine a line, if you will. And the reason I say with different x's is I feel uncomfortable with lines of infinite slope. In a stat class, a line of infinite slope says there's only one value of x. The y's may be all over the chart, but only one value of x, and that's not much of a study to look for an XY relationship. So you would naturally pick two different XY X values and then find the average Y. So I'm thinking I have X1 and X2. Now those could be 1 and 2, 0 and 1, 50 and 100, 3 and 12. I don't really care what they are, but those are two different levels of X. And there's, if you will, mu for X1 and mu for X2, mu1 and mu2. But if I felt like it, I could say, you know what? It's really a straight line. Beta 0 plus beta 1 times x. That is the value of mu for any value of x I could choose. A straight line relationship, or two separate means, one for each of the x levels, they're the same thing. You might have even noticed that some of the data sets that I've given you have accidentally had values for x of like 0 and 1. Or maybe it wasn't accidental, maybe it's on purpose. If x1 was 0 and x2 was a value of 1, the run here is 1 unit. The rise is the slope. Beta 1 equals mu2 minus mu1. Literally, it's how much higher is the second mean than the first. Now that sounds like an effect where x equaling 1 is the reference group, and how much higher is mu2 than mu1, the reference group's mean. So, two different x's, a trend line, or two separate values for the average y for each of the x's. What are some reasons why you might prefer a straight line to simply having two different values, mu1 and mu2, and not knowing the linear trend? What does the linear trend buy you? This is where I look around the room, and usually there's someone in the back raising their hand, but it's not happening in class these days much. Just unmute yourself, someone. And maybe as an example, if x1 were a height of 5'5", and x2 were a height of 5'10", mu1 is the average weight of people who are 5'5", and mu2 is the average weight of people who are 5'10". What would a trend line get me that just knowing the two average weights for the two given heights wouldn't tell me?
It would allow you to interpolate and estimate other values.
There you go. For any height out there, I could tell you the average weight of someone of that height. And interpolate, I love the word, because between x1 and x2, it seems like it's just connect the dots and really don't go out past that range. The data would be clearly speaking in that middling range. Or if I'm going to extrapolate, extrapolating a little bit in a range which would be presumably linear, seems fine to me. Okay, so that's a win, isn't it? Okay, so I would probably prefer a slope model with two values of x that are quantitative if I thought that there was a linear trend. I'm going to clear this and consider a slightly different question. What if I've got three separate values for x, x1, x2, and x3? And I'm drawing these such that they're not necessarily equally spaced apart. You could think different dosages of a medicine. x1 could be no medicine is given. x2 is a normal amount of the medicine is given, and x3 could be corresponding to a level of, well, what if we give triple the typical dose? Okay. And if I have mu1, mu2, and mu3, I'm thinking a straight line isn't all of a sudden very good anymore. But I also think, sometimes if you give people too much medicine, it could be bad. A small amount good, a lot bad. Thinking back to high school geometry, any 2 points can form a straight line. Actually, let's talk about this in terms of not geometry, but algebra 1 or perhaps algebra 2, depending on, when you saw it most recently is probably the way you remember it. But in algebra 1, remember that any 3 separate values, x1, x2, and x3, and the corresponding y values that go with those, there is one unique parabola, a quadratic, if you will, that perfectly goes through all 1, 2, 3 data points. So I'm just going to choose to draw this in, and this is not going to be perfectly parabolic, but I'm going to try my best. Well, until I got to the very end, it looked good. Okay, there we go. Almost fixed it. Did it look like I at least attempted to draw a parabola? Okay, the attempt has been made. My claim is 3 separate points, x1, x2, and x3, a parabolic or quadratic relationship will perfectly describe that trend. Now, I'm no longer going to rely on some sort of statement of, oh yeah, you know, it's perfect now. But if I was open to believing a quadratic model would make sense, there's going to be beta 0 plus beta 1 times x plus beta 2 times x squared. That self-interaction or quadratic model would perfectly describe the data the exact same way that 1, 2, 3 separate means, mu1, mu2, and mu3, would explain. 3 separate average values of y for the 3 distinct x's I could fit perfectly with a quadratic. So let's over here on the right keep track of something. Number of x's, and then the sort of model, the polynomial model. 2 x's, I get a straight line beta 0 plus beta 1 times x plus, well, that's it. So let's go ahead and go back a little bit. If I've got 3 separate x's, quadratic beta 0 plus beta 1 times x plus beta 2x squared will perfectly fit. And I guess I could still interpolate or extrapolate, but again, it's having to still believe a model, in this case, a quadratic model. But if quadratic made sense to you as the expert in the discipline, sure. If you believe somehow that the levels of rainfall, there's a maximum level of rainfall that's considered ideal for plants, and rainfall levels that are too low or too high have a parabolic relationship, you could say, okay, I'm good with that. So what if we were to go ahead and try 4 separate levels of x? Okay, so erase all that, or better yet, just clear the whole thing. 4 separate levels for x. x1, x2, x3, and x4. Now, I don't know that that looks like it's easy, but via analogy, if 2 points determine a straight line and 3 points determine a quadratic, 4 points could determine a cubic model. So what would that cubic model look like? Well, this is where my life gets challenging here, but remember cubic, if it's perfectly cubic, it's got sort of like it goes up and then down, then up again. Okay, I have to have the up and the down and the up again, so it can perfectly go through all of these values, up and then down and then up again. Yeah, maybe. At least an attempt at drawing a cubic has been made. And I'm going to make the claim that, yes, it's a perfectly matched fit. Similarly, if I had 5 x's, 5 distinct x values, a quartic model, x to the 4th power, x cubed, x squared, and x by themselves are the terms that would perfectly match what's going on in my data set. Okay? So that's my argument. Let's go ahead and show you in the context of an example. And here's a data set that I've got on the fat acidity in flour across multiple separate weeks. Okay, so there were 12 separate different methods for processing flour that were utilized, and we're measuring the level of fat acidity across time in the flour after it was processed. And I guess there's different types, okay, of flour that were created. We're using methods 2, 3, 4, and 9. 2, 4, 7, and 9 are shown here. There were 12 separate methods. And I'm ignoring differences across the different types of processing the flour, just looking here at the methods. Okay? So if I'm looking at these data here, it seems like I've got, 1, 2, 3, 4, 5, 6 separate levels of X. My claim is a categorical fit, or X squared, X cubed, X to the 4th, and X to the 5th all could match the exact same fitted values, the exact same trend. So pick a color. Anyone got a favorite color of these 4?
Purple.
Purple. We're doing purple now. Okay, so I'm going to take everything but the purple. The purple was method 9, so I'm going to basically highlight method 2 and say, select the matching cells and hide and exclude those. Method 4, hide, select those matching cells, hide and exclude those guys as well. 7, select all the 7s, and then hide and exclude everything but the 7s. Okay, so what we've got now is just method. Oh, shoot, did I do 4 and 9? Darn it. Ooh. There's a bit of an error here somewhere. Method 4 is still showing. Okay, so I'm going to select method 2 because that looks like it's a bit of an issue here. I'm going to select all the matching cells and again hide and exclude, and I'm going to do 4 just again one more time. And this time hopefully I'll do it right. And we're left with just method 9. It used to be in purple, now it's in a slightly different color perhaps. Bluish. My method 9 in blue. I claim that for just this data set, just method 9, I could fit a 1, 2, 3, 4, 5, 6 mean model. Let me turn off that smoother. I could have 6 separate values for the 6 separate averages, okay? Or I could fit a polynomial. Let's show you how to do each of those different approaches. Okay, so under Analyze, Fit Model, my claim is if I take method as categorical, okay, and weeks as, no, better yet, weeks as nominal, if I turn weeks to nominal, a categorical variable, I could say weeks, the log of the fat acidity, that's what we're showing here, the log of fat acidity, because that looks more linear. Doesn't it look like there's just one outlier, doesn't it? Other than that, it looks like it's maybe a slight curve, but that one outlier messes stuff up. Log fat acidity depends on weeks, and weeks here as categorical. If I were to run that analysis, I get, well, lots of different ways of viewing things, but let's focus on what we're going to later compare to our rerunning in this other fashion. I've got my ANOVA says 0.5624, my R squared 0.414. I'm not seeing it as statistically noticeable a difference across these 1, 2, 3, 4, 6 separate levels for weeks 0, 3, 6, 9, 15, and 21. I don't see weeks as mattering. Okay, but I get a set of predicted values. I could even choose to save them if I wanted to. So under Save Columns, save the predicted values. Those are the fitted values, if you will, the y-hats. And I'm noticing here, I need to make this bigger. Now I have for each of the different weeks the predicted value, and notice that it's filling in a predicted value for even other methods. Method 1, 2, 3, 4, 5, 6, 7, 8, 10, 11 all have the same predicted fat acidity because I said do not use any of those XY pairs in your analysis. Only use method 9 data. And so if all I have is method 9 data, if it is week 0, I'm predicting the same average fat acidity. So I've got these predicted fat acidity levels. I could fit the model, my claim is, differently. I could fit a polynomial. Now there are 6 separate levels for weeks. Again, weeks 0, 3, 6, 9, 15, and 21. So 6 different levels for weeks. Let's go ahead and fit that model as though it's quantitative and fit it comparably. So I'm going to go ahead and fit model. I'm going to click recall, and where it said weeks here, notice that if I said weeks now, let's make it continuous. That would fit a linear trend. I would also want weeks squared, weeks to the power 2, weeks cubed, weeks to the power 3, weeks to the 4th power, 5th. Yeah, I would need all of those. So let's go ahead and try with macros. Remember the polynomials? Yeah. To degree 5. I want to have a polynomial for weeks up to degree 5. Weeks, weeks squared, weeks cubed, weeks to the 4th, and weeks to the 5th. My claim is it should fit the exact same model. Now here is a situation where I think centering makes sense to me. I prefer the centering in this context. You don't have to if you don't want to. Okay. The way our textbook tackles this is with Minitab, and Minitab does not, by default, center. And that's the nature of that one homework problem in Chapter 10 that I may or may not assign, I may or may not rewrite. Okay? So centering the polynomials, we're going to center because it's JMP, and I think there's a preference to doing that. If I were to run the analysis, we see, well, the results look a little different. First off, we get our graph up the top. That graph looks different because it does the fitting of the polynomial and displays the polynomial that was just fit, allowing us for visual use to say interpolating between 0 and 3 weeks or between 3 and 6, we sort of know what we're thinking happens. You have a sense for what the fit should look like for the interpolation at least. Extrapolation with a x to the 5th power seems like a mistake though, because that's going to balloon up really quickly. Okay. So I'm going to ignore that and that and that. Focus in on just the things that we said we would want to compare later. I'm spotting r squared is the same. Exactly the same. The root mean square error 0.26032, 0.26032, that's the same. Notice my analysis of variance for the overall model with 5 degrees of freedom for the 6 categorical levels of the categorical version of weeks resulted in an F ratio 0.8480 and a p-value above 0.05. If I have the quantitative version with weeks, weeks squared, weeks cubed to the 4th, and even weeks to the 5th power, still 5 degrees of freedom. Look, 5. Same sum of squares is over there. Same mean square. Shoot, same SS error, mean square error, same F ratio. Same model was fit. The question is, how do we look at the model? Do we want to choose to look at the model as one where it's a polynomial and we can interpolate, or do we want to simply say, oh yeah, there's just these 6 different weeks at which we measured, and there's separate average levels of y for each of those 6 weeks? Does it matter? Earlier today, Claire said, yes, it does. Why would this be different, these two analyses? There's one reason. I can interpolate. If we have a factor that is numeric or quantitative, fitting it as such with all of the corresponding polynomials gets you an identical fit, and you can interpolate. But there is an additional benefit. And for that additional benefit, I want to just go ahead and turn on the sums of squares that are sequential, the sequential tests, if you will. Down at the bottom, the sequential tests, I can now say, if I control for all the higher up in the table terms, if I control for weeks, even a quadratic or a cubic or a quartic version of weeks, do I need weeks to the 5th power? No, I don't. So we could remove weeks to the 5th power. And could I even say, controlling for weeks, weeks squared and weeks cubed, do I need weeks to the 4th? No, you don't. What about controlling for weeks and weeks squared? Do you need weeks to the 3rd power? There's no evidence that it's helping us. Do you even need a quadratic curvature term? Controlling for a linear trend overall, is there any benefit of having a quadratic? No, there isn't. And like lab from Tuesday, you could even test these all simultaneously. You could drop out weeks squared, weeks cubed, weeks to the 4th, and weeks to the 5th, and see if any of them would be helpful. You aren't limited to doing sequential tests. We could literally compare the model with a linear fit to the model with absolutely the 5th order polynomial and say, do any of the higher order terms at all matter? One additional thing I want to mention before we summarize and turn you loose on the lab, and that is this. There's not just the benefit of interpolating. There's not just the benefit of saying, hey, we've got this fancy polynomial and we can test these higher order terms. What would happen if I eliminated the higher order terms? My claim is this. If you eliminated weeks cubed, weeks to the 4th, and weeks to the 5th, if you eliminate unnecessary higher order terms, that will not increase the sum of squared error by much. But it will increase degrees of freedom for error. And so if your numerator isn't changing upwards quickly, but your denominator is changing to be growing, the mean square error should be decreasing. And if the mean square error decreases, the F ratio should tend to increase. That means that if you fit this model as to the 5th order polynomial, and then you don't need the cubed and the squared and the 4th and the 5th, if you could get rid of these higher order terms, you may be more likely to be able to spot a linear trend if one exists. Or if there was possibly a quadratic trend that was only slightly quadratic, you might be able to spot it as statistically noticeable if you've eliminated the cubic, quartic, and quintic terms. I want to go ahead and try that. And with this data set for just this treatment, I haven't tried it yet, but we'll see what happens. I'm going to go ahead and fit model. Recall is your friend. I still have week as quantitative. But notice I've got weeks to the 5th, weeks to the 4th, weeks cubed. If I decide I want to delete weeks cubed, it's going to say, oh, by the way, do I want to also eliminate weeks to the 4th and weeks to the 5th? And I just say typically yes. This is a reminder that we want models that are hierarchical. Literally, if you eliminate base terms, you should not keep the fancier terms, which include those base terms in them. You need the base parts to build a wall. You know, you have to have the two basic bricks before you put the one on top of them. Okay? If you eliminate one of the basic things, you probably should also remove the bricks on top of them, or else things will fall down. I click yes, eliminate all those higher order terms. So I got a model with quadratic, weeks squared. I'm going to run that analysis. It's still not going to be great. I mean, to be honest, here's the model that we fit. It does look pretty good. It's a quadratic. There is this wrinkle here. That seems to be a bit of an issue. But overall, how is my model doing? R squared dropped a lot. My ANOVA, though, notice that my mean square error formerly was a 0.07. Now it's 0.06. Not a dramatic decrease. Not a dramatic decrease, he says, better. I didn't decrease SSE much, or increase SSE much, but the change in degrees of freedom decreased mean square error. Mean square for the model went up a little bit because of fewer degrees of freedom. Mean square error went down a little bit because of more degrees of freedom for error. The F ratio now is larger. My corresponding p-value is smaller. Let's try that sequential analysis. My p-value earlier for my sequential analysis said I have no proof or evidence that there is a benefit of weeks, and given weeks there is no benefit of weeks squared. I'm sorry, I apologize, that was wrong. Those are not the p-values. There is no evidence of weeks mattering, and there's no benefit of having weeks squared. We hit the same conclusions here, but notice my p-values have each decreased a little bit, just like my overall model p-value has decreased. Okay, so quickly, the three benefits of these polynomial fits to quantitative factors. Instead of fitting them as categories, fit them as a polynomial. Interpolation, extrapolation, 1. 2, you with those higher order terms, you literally can test them and see if you need them. And if you don't need them, get rid of them. For model parsimony, the model which is smallest with the fewest complex terms, if it still explains the trend, it is your best model. Why? Because that will tend to increase your F ratios for the terms that remain. Okay, so let's try and summarize all that. We've got our trend here, and if our trend is quadratic or cubic, we can fit it just as well with the quantitative version, the polynomial version, as we could with categorical fits. Okay? But if there is a problem, using sequential sums of squares, we can make our model simpler. And with a simpler model, we can really tell you, no, you don't need the complexity. It's definitely not as good, which increases our ability to spot factors that are important. Okay, I think that's about where I wanted to finish off today. Other than, well, next time we'll talk about model hierarchy. I think that's probably better put on hold for a little bit. Okay. Any of you have questions on any of that, or would like me to rephrase it or address a point? Okay, so it's lab time, and the lab you've got, and I've got a confirmation from at least one of you that you got the lab, so that's good. And then it's on horse semen again. You are going to go ahead and try fitting a model 2 different ways. I believe I have the variable in there in 2 separate ways. One is quantitative and one is categorical already for you. One is called hours and one is called minutes. But if you take, hours and multiply by 60, don't you get the number of minutes? And so if one of them is quantitative and the other is categorical, like 0 hours, 1/2 of an hour, 1 hour, 1.5 hours, if that's categorical, but the minutes is quantitative, or the other way around, you don't have to sort of change the variable from quantitative to numeric. Numeric to categorical, back and forth. Just swap the one variable out, and you can find the same fitted values. And that's the point of today's lab, is grabbing onto that. Okay, so I'm going to stop the sharing. I'm going to stop the recording and turn you loose on the lab.